Let's talk about the size of ions. We've already learned about atomic sizes, and the atomic sizes I will show you on another picture. Okay, here's a diagram of atomic size according to where they are in the periodic table, and we noted that as you go down a group, size gets larger, and that as you go across a group, size gets smaller, which means it gets larger going to the left. So size is the largest in the lower left-hand corner. All right, now let's compare that to ions. So that's neutral atoms. And now we'll go back and talk about ions. Okay, so if we'll compare it to atomic size. So sodium atom, if it's some size, which I've drawn by this circle, then you go across that same period and you'll get to a chlorine atom, which is smaller. Because you go across a period, it gets smaller, right? So decreases across a period. And that's for neutral atoms. Okay, but now if you take a sodium atom and remove an electron, you have sodium plus. That electron comes from the outermost orbital. So sodium plus is smaller. Okay, remove an electron, minus an electron. If you take a chlorine atom and add an electron, it's much more loosely held. So we add an electron, and so Cl minus is much larger than chlorine was. So even though as a neutral atom, chlorine is smaller than sodium, when you form ionic compounds, the chlorine is now larger than the sodium, and it's now chloride. Okay, so the sodium lost one electron, and since it lost an electron, the way we talk about it is we say the effective nuclear charge has now increased for the remaining electrons, because they each feel the pull of the protons in the nucleus more. Okay, so we say our effective nuclear charge, or our effective atomic number, is now greater because we have ionized it. So the electrons are held more tightly. Whereas for chlorine, it gained an electron, and so those that last electron is held more loosely. So it makes a much larger ion. Okay, so let's look at trends. First, going across a period. As you go across, you have separate trends for the cations and anions. Okay, the cations are the positive ions. So sodium plus then has some size. Magnesium, when it forms a cation, is 2 plus. So it's lost 2 electrons, so it shrinks even more. And aluminum, going across, 3 plus, shrinks even more because from its original, because it has lost 3 electrons. Then if you jump across to anions, the chlorine has now become chloride ion, and so it's bigger than it originally was. Sulfur takes on 2 electrons, so it's even bigger, and phosphorus takes on 3 electrons to form an anion, so it's even bigger. So you have this trend where it's decreasing size within the cations and decreasing size within the anions, but there's a big jump between cations and anions. Okay, so using this information, we can say look at these problems and decide which is larger, magnesium or phosphorus. Okay, as a neutral atom, magnesium and phosphorus are in the same period, so as you go across the period, they're going to get smaller, so magnesium is going to be larger. But when you compare magnesium 2 plus to phosphorus 3 minus, the ions, the anion is much larger. Okay, next one, looking at neutral atoms, potassium and bromine. You're going across on one row, so the potassium is larger. But once you make them ions, potassium shrinks, bromine gets larger, and it gets larger enough that it is the largest of the two. Okay, so when we make ions, when we make positive ions, we have to remove an electron, and there's an energy involved in pulling that electron off, and that's called the ionization energy. Okay, and we can abbreviate it IE. So that's the energy needed to remove an electron. It's always positive because it always takes energy to remove an electron. Takes energy to remove an electron. All right, so the process can be written like this. Sodium gas, and that's meaning that it's a single sodium atom, becomes sodium plus, and we're going to write it as gas again, plus an electron. And that is the ionization process. You can also, and that happens readily for sodium because it will attain a noble gas configuration. But you can talk about ionization energy for any atom. Okay, so chlorine as a single atom can also become chlorine plus an electron. And this energy involved will be the ionization energy, but it's going to be much larger because chlorine would be energetically more favored to take on an electron rather than lose an electron. So the ionization energy to take one off sodium is low because it readily does that and becomes a noble gas configuration, whereas chlorine has an ionization energy that is much larger. So we can talk about trends in ionization energy just like we did in size, and ionization energy gets larger as you go across a period, and it gets smaller as you go down, so it gets larger as you go up. And part of that reason is for the group trend is that you're getting bigger and bigger ions as you go down, so it's easier and easier to remove an electron. Okay, so the ionization energy is large in this corner because it's hard to remove an electron. Okay, so large ionization energy means that it's hard to remove an electron. It takes lots of energy to remove the electron. All right, let's practice this. Which one has a lower ionization energy? In other words, which one is it easier to remove the electron? All right, so try this. Sodium or chlorine, those are on the same period, and as you go across, it's going to be harder to remove the electron. We already said sodium was easy to remove it because it will attain a noble gas configuration. Chlorine would much rather take a new electron than give one up, so it's got a much larger ionization energy. Then if you look at fluorine or chlorine, that's the trend going down a group, and it's definitely going to be easier for a larger atom to remove an electron because it's held more loosely. So chlorine's a larger neutral atom, and so it's easier to take off an electron, which means a lower ionization energy. Okay, we can remove more than one electron. Okay, we just talked about taking sodium and removing one electron, making it sodium plus, and that energy would be referred to as the ionization energy. Okay, and to remind you, we have a configuration of neon 3s1, and it becomes just neon. Okay, so it's happy there. Okay, it's happy at neon. Very happy being Na+. But that doesn't mean we can't take another one off. We can take sodium plus, like we've made here, and take another electron off. Okay, take the electron off, make it 2+. We refer to that energy as IE2. Okay, so this one is IE1 or just IE. And then we can keep pulling off more electrons. As long as there's still electrons present, you can keep pulling them off. Sodium has 11 electrons, so we could pull off all 11. And the energy would be greater and greater as we pull them off. If you start with Na2+ and pull off another one, that energy will be IE3. Okay, so what do those energies look like? If we graph those energies, IE or IE1 would be some energy. We're not putting any units on this. We're just doing a qualitative look. The ionization energy for sodium would be some value. Once you take off that electron, it's happy there. The next electron would have to come out of the neon rare gas or noble gas configuration. So it's not going to be easy to pull the next electron off. This one here is neon. Okay, it's not going to want to pull one out of there. It wants to stay neon. Okay, so the next ionization energy is going to be much higher. And the next one's higher and higher, but they aren't going to have nearly as big a gap. Okay, IE4, and so on and so forth. There's a big gap here because after you took off one electron, it was fairly stable, and then to pull off any more takes a lot more energy, so there's a big gap. Let's do another example of that. Let's look at boron. For boron, here's its configuration. It has 3 valence electrons, so those first 3 are not going to be that hard to pull off. Okay, so it will have some value for ionization energy, and I'll mark it as 1. It'll have some other energy higher for ionization energy 2, and another one for IE3. And if you try to pull off that 4th electron, you will then have helium at that point as your configuration. It'll be a lot harder, so there'll be a big gap there, and IE4 will be much higher, and then IE5. Each successive ionization is always higher, but you'll see a big gap at the point when you're trying to take one out of a rare gas configuration. Or noble gas configuration. Okay, so that's going to be harder. All right, another process that's somewhat similar. Ionization energy was taking an electron off. Electron affinity, which we abbreviate as EA, is the energy of taking an electron and adding it to something. All right, and most of these energies are negative, which means it's more favorable to have that electron put on. Okay, so let's look at fluorine. Fluorine, you add an electron, you make it F-, and it's happy because it's got a noble gas configuration. So that's a negative energy, meaning it becomes more stable when you put it on. And most electron affinities are negative. Not all, though, you'll see in a minute. Okay, so the noble gases will have a positive, I said most of them are negative. The noble gases have a positive electron affinity because they are happy with their configurations. They don't want an additional electron, so you have to give it energy to make it take an electron. I also want to point out that electron affinity is not the opposite of ionization energy. Okay, ionization energy was if you take the same fluorine atom, if you take a fluorine and you take an electron off, it becomes F+. So the opposite is not this process. You could, it's not taking S+ and adding an electron, it's taking F and adding an electron. So it's not the same thing. Keep those straight. Although you certainly could talk about the electron affinity of F+, but the electron affinity of F is the neutral atom. All right, so here are the trends in electron affinity in this chart. Notice that, like we said, the noble gases are all positive. Okay, they're all above 0. We don't have values there. And a lot of them are negative. Most of them are negative. There are a few exceptions. Okay, what are the exceptions? The exceptions will occur when you have a full s orbital or a full p orbital or a half full p orbital. Remember, a half full p orbital looks like this. Okay, and even though it's not full, there's some stability in having a half full orbital. So a fully full p orbital is here. Those are positive. A half full p orbital, one example is nitrogen. The lower ones are different, but nitrogen is positive because it's a half full p orbital, and then the full s orbitals are positive or very small. Okay, so these are the things that are going to be, in general, positive. But most atoms will be negative for electron affinity.